All right, so what we're going to be looking at here is some definitions and theorems, specifically definitions and theorems revolving around exterior, interior angles, and then also those that are revolving around triangle inequalities, okay? Now, I wrote these out ahead of time, so again, if you want to hit pause, then you can write this down and then hit play, and then you can write down the example or the diagram, and then listen to the explanation over it. So in the first one here, we have the definition of the exterior angle, and it's an angle that forms a linear pair with one of the angles of a convex polygon. So remember, a linear pair, we're talking about two adjacent angles that form a straight line that add up to be 180. Okay, now in the context of what we're focused on those that are involving triangles. Okay, so let's say I have this example here. Okay, now this guy right here, that's our triangle, right? But I'm extending out these rays so that we can actually see where the exterior angle comes into play, okay? So let's call this angle 7. We have 2, we have 1, 3, 4, 5, well, better 5, and a little bit better, and then 6, okay? So we have these guys right here. Now, when we're talking about an exterior angle, okay, they have to form a linear pair. Just go back to our definition here. They have to form a linear pair with one of the angles in our polygon, okay? Well, for instance, notice angle 7 and angle 2. Do those guys form a linear pair? Yeah, they're adjacent angles and they form a straight line. So angle 7 here, that would be an exterior angle, okay? Well, also notice angle 3 and angle 4. Are those guys adjacent angles that form a linear pair? Yeah, so angle 4 would be an exterior angle, okay? Well, also notice with the ray that's also extended out on the other end here, let's use pink, okay, is angle 3 and angle 6 here. Those guys are adjacent angles, correct? Well, angle 3 and angle 6, do they form a linear pair? Yes, so angle 6 here, that would also be an exterior angle. However, would angle 3 and angle 5 here, would those guys count as a linear pair so that angle 5 would be an exterior angle? Well, no. Notice angle 3 and angle 5 here, those guys separately as two separate angles here. Okay, so angle 3 and angle 5, those guys, just from the very get-go, they're not even adjacent angles. We don't even have adjacent angles here, so let alone they can't form a linear pair. So angle 5 here actually is not an exterior angle. So the only exterior angles we have here is angle 7, which forms a linear pair with 2, angle 4, which forms a linear pair with angle 3, and angle 6, which forms a linear pair with angle 3. Okay? So those guys would be our exterior angles, okay? Now, every vertex has the possibility of 2. Notice we had 2 here, angle 4 and angle 6. At that vertex, form linear pairs with 3. So every vertex has 2 possible exterior angles. Two possible exterior angles. But in our examples, okay, angle 4, angle 6, and angle 7 are exterior angles. And I'm going to abbreviate it, but those guys were our exterior angles. And remember, angle 5 was not, because it doesn't form a linear pair with one of our inside angles there, okay? It didn't form a linear pair with angle 3. It wasn't even an adjacent angle with it. Okay, so angle 7, 4, and 6, those are the exterior angles. Now, those on the inside that we didn't really give a name, so go back to those angles that are the inside of our triangle. Well, there's a specific group that we can talk about, the remote interior angles. And the interior angles, based on our definition here, the interior angles of a triangle do not form a linear pair with a given exterior angle, okay? Now, we're focused on the angles that are inside the triangle, but they do not form a linear pair with one of the exterior angles given, okay? So let's use another example here. And again, I'm extending these out to raise just so that we can see these exterior angles. But maybe we call this 1, 2, 3, 7, 6, 5, and 4. Okay, so in our example here, okay, notice angle 3 and angle 7 here, do they form a linear pair? Yes. So angle 7 is a what? Well, based on what we just learned, by its definition, that guy would be an exterior angle. Angle 7 is an exterior angle. Now, angles 1, 2, and 3, they're on the interior, the inside of our triangle. However, we're wanting to know the remote interior, okay? The remote interior angles are those that do not form a linear pair with 7. Well, which angle formed a linear pair with 7? 3, right? Angle 3 and angle 7 form a linear pair. Which angles on the inside do not form a linear pair? 1 and 2. Those guys do not form a linear pair with 7, okay? So those guys, angle 1 and angle 2 here, they would be the remote interior angles of angle 7 here, okay? They're the remote interior angles for angle 7. Not necessarily any other exterior angle, but for angle 7 here. Okay, and then similarly, let's look at the other exterior angles we have. Remember, angle 6 over here, is this guy an exterior angle? No, because it doesn't form a linear pair with 3, right? However, does angle 5, does this guy form a linear pair? Yeah, so angle 5 is an exterior angle. Now, based on what we have for angle 5, since it forms a linear pair with 3, 3 would not be a remote interior angle, okay? It's an interior but not remote interior. Which two angles on the inside do not form a linear pair with 5? 1 and 2. So in this case, 1 and 2 are both the remote interior angles of both angle 5 and angle 7, okay? What's the last exterior angle that we have here? Well, that would be angle 4, right? It forms a linear pair with angle 2. So if it forms a linear pair with angle 2, what's its remote interior angles, the ones that do not form a linear pair? Well, that would be 1 and 3, right? So a good way to think of this is, if you know where the exterior angle is, it's the two interior angles opposite that angle. Okay, so notice 2 formed a linear pair with 4, but that's not the remote interior. 1 and 3 are the remote interior angles to angle 4 here. Okay, so let's write that out so that we have this on our definitions here. Okay, so with respect to angle 4, okay, that just means if we're talking about angle 4, the remote interior angles are angle 1 and angle 3. So remember, we said in our example here, if 4 is our exterior angle, then angle 1 and angle 3 are the remote interior angles, okay, the ones that do not form that linear pair. Okay, then similarly with respect to angle 5 or 7, because it worked for 7 too. Remember, angle 7 had the same remote interior angles. The remote interior angles, I'm going to abbreviate it, those guys are angle 1 and angle 2. Okay, so for both 5 and 7, so for 7 and 5 here, the remote interior angles were angle 1 and angle 2. Okay, now it's important to know that because they play a large role in what we're talking about in these theorems. So that's what they are. Now let's talk about what they mean in terms of our theorems. Well, the first guy that I see here is the exterior angle theorem. Now, the exterior angle theorem says the measure of an exterior angle of a triangle is equal to the sum of its two remote interior angles, okay? So all that means is if I have a triangle here, and we extend one side out as a ray so that it forms an exterior angle, let's say this is 1, 2, and 3. These are the interior angles, and 4 is our exterior angle. Well, then the two remote interior angles, they add to be the same measure as angle 4. Well, what's the remote interior angles here? Angle 1 and angle 2, because they do not form a linear pair with 4, right? 3 does. 3 forms a linear pair, but 1 and 2 do not. So all that means is, this is what you need to know, okay? The measure of angle 1 plus the measure of angle 2 equals the measure of angle 4. And we could prove this if we had time here, but just know this. Angle 1 plus angle 2 equals angle 4. Okay, that's all you really need to know there, is that the two remote interior angles add up to be that guy. And that plays off of our linear pair relationship. Okay, T26, okay, the measure of an exterior angle of a triangle is greater than the measure of its two remote interior angles. Now, this is one of those theorems that I say are the duh theorems, like no duh, okay? Go back to this. If angle 1 and angle 2 add to be 4, doesn't that mean 4 is bigger than either one of those? Yeah. For instance, 2 plus 3 equals 5. Isn't 5 bigger than 2 and 3? Yeah. So that's one of those no-duh theorems. Of course, the exterior angle is going to be bigger than either one of those, okay? Now, we could kind of draw a figure to represent that, but all that's saying is if I have our exterior angle with a triangle here, maybe we still keep this as 4, 3, and maybe this is 1 and 2, okay? Then the measure of angle 4 is going to be greater than the measure of angle 1, and the measure of angle 4 is going to be greater than the measure of angle 2, okay? All it's saying is the measure of angle 4 is greater than the other two of that remote interior angles, okay? Now, T27 here. If the measure of the sides of a triangle, let's put it in perspective here, if the measures of the sides of a triangle are unequal, so we have unequal sides, so we're talking about a scalene triangle, are unequal, then the measures of the angles opposite those sides are unequal in the same order, okay? Here's an easy way to think of it, okay? If we have a triangle that has different sides, maybe the sides are 3, 4, and 5 or something like that, then their angles opposite those sides would also be in the same order from least to greatest, okay? So whatever it is from least to greatest for the sides, it's going to be in the same order opposite those sides from least to greatest, okay? So in T27 here, maybe I have some triangle like this, okay, where we have M, P, N, and let's say this side is 6, this side is 18, and this side is 11. Well, notice all the sides have different measures, okay? Let's just write that what we know. We know that PN is the smallest side of 6, so PN's measure is the smallest, and it's less than, what's the next biggest one? MP, right? So it's less than MP, which was 11, and MP, what's the next one that's biggest? MN, right? So the next biggest one is MN, which was 18. So notice PN side, which is 6, is smaller than MP sides, which was 11, which is smaller than MN side, which is 18, okay? So what this theorem says is, notice, it goes from smallest to the next largest to the next largest. Well, the angles will work in the same way, the angles that are opposite those sides. So what's the angle that is opposite PN? Angle M, right? Angle M is opposite this side here. It's the angle that is going to be the smallest in the triangle, okay? So angle M is going to be the smallest. The measure of angle M is going to be the smallest angle. And it's going to be less than this guy's angle that is opposite MP, okay? Well, what angle is opposite MP? Well, here's MP. What's the angle that's opposite? Angle M. So that would be the next biggest angle. Okay, that would be the next biggest angle. The measure of... it's starting to get confusing here, but no, this guy is supposed to be our inequality sign. This guy is supposed to be our angle there, so please don't get those guys confused. I'll try to make it a slight difference here, maybe. Okay, that's supposed to be less than. Then this is the measure of angle N. Okay, which is going to be less than the next angle. Okay, well, what's the last angle here? The measure of angle P. Okay, whoops, that did not work. There we go. Okay, now notice, look at angle P over here. Okay, it's opposite MN. That's the largest side, so this is going to be the largest angle. Okay, it's opposite the largest side, so it's the largest angle. Okay, that's all this guy is saying. Another way to put it into words is the smallest angle is across the smallest side. Or shortest side. Okay, so if the measure of the sides of a triangle are unequal, then the measures of the angles opposite those sides are unequal in the same order. Now T28 is pretty similar. It says if the measures of the angles, so now it's just saying the angles of a triangle are unequal, then the measures of the sides opposite those angles are unequal in the same order. So it's basically the same thing, just in reverse. So in this case, they're giving you unequal angles, and then the sides opposite those would be unequal in the same order. Okay, so maybe we have some triangle like this, where we have K, W, and then we have J. And let's say we have our smallest angle is 35 degrees, then we have the next angle is 45 degrees, then we have the next angle is 100 degrees, okay? Angle K is the smallest, right? So angle K is the smallest. Well, what side is opposite angle K? WJ, right? So WJ would be the smallest side. Okay, so let's just write this out. We know that the measure of angle K is the smallest, and it's less than the next biggest measure, which is angle W, the measure of angle W, and that's smaller than the largest angle, which was measure of J, which was 100 degrees. Okay, so that's the order of the angles. Then the sides would follow suit. So we said that WJ's measure would be the smallest, and it'd be less than the next biggest angle. Well, the next biggest angle is 45 degrees, okay, this guy here. Well, what side is opposite 45 degrees? KJ. So that would be the next guy. The next biggest side would be KJ. And then the next biggest side would be the largest side, which is opposite 100. So 100 is the largest angle, so KW would be the largest side. Okay, so KW would be the largest side. Okay, that's all it's saying there, and it's the same thing. The shortest side is across the smallest, or the shortest angle is across the smallest side, and the smallest side is across the shortest angle. Same thing. Then we have T29 here. Okay, in a right triangle, the hypotenuse is the side with the greatest measure. Well, duh. Okay, that's another one of those duh things that you guys already know. We have a right triangle here. Okay, the hypotenuse is the largest side of a right triangle, and it's opposite. Notice it's across the right angle. Okay, it's across the right angle. Okay, then the triangle inequality theorem. Okay, this guy's going to show up as well, and it says the sum of the measures of any two sides of the triangle. So you pick any two sides of the triangle. If you add those sides together, it will always be bigger. Whoa, something fell. That will always be bigger than the third side. Okay, so the sum of the measures of any two sides of a triangle will always be bigger than the third side. So if I have this guy, maybe we have A, B, and C, A, B, and C, okay, then A plus B would be greater than the side C. Similarly, B plus C would be greater than A, and then A plus C would be greater than B. Okay, so all that means is if you add up the lengths of any two sides, it's always going to be bigger than the third side.